Okay, Paul here, and today we have on the bench a Gilfillan Brothers Inc. radio, model 56C, and there's the front of the radio, and the customer's complaint is that it has a hum, which we understand that would be filter capacitor. The dial, as you can see, is skewed, so it needs to be straightened out. And the volume control knob is hard to turn, so we're going to see if we can clean that up and get that turning a little better. The unit is in great shape. It's got a very small hairline mark here, and a little tiny crack here. It's got a little bit of staining, but overall this radio is in beautiful condition. Got some neat wave lines through it on the side here. I don't know what those are, but they're interesting. Anyway, so we're going to go ahead and take it apart. It's a nice ivory colored radio, and it has a ivory colored cord and a nice vintage plug. Seems to be in pretty good shape. Could use a little cleaning, but the cord is not brittle. Doesn't appear to be cracked anywhere. And I'll hook that up to a variac and current limiting bulb. But let's go ahead and see about getting this unit out of the chassis. It's a well-made case. It's got screws on the bottom. Okay, let's take it out and see what we got. Start with the knobs. Now when you take the knobs off, you got to be very careful. Some of these knobs have not been removed in a very long time. This one is not only tight to turn, it's tight to get off. And I'm going very slow with it, because you don't want to break that aged plastic. There we go. It has a nice tight metal clip in there. They did things a lot differently in the 40s. Let's see what the schematic says on this. It doesn't seem to have a date on this schematic, but there it is, 46. Well, it was in Ryder's schematics in July. It was added July 28, 1946. So it's December 28, 1946. So it's probably a 46, maybe a 45. Let me get a little bucket here to put some parts in. Always keep screws and things in a little box so you don't lose stuff. Looks a little better. It doesn't seem like these screws have been out in a while, if they've been out at all. Get them started with this screwdriver. Apologize for the noise in the background. That's my little space heater. It's pretty cold out, so I gotta have some heat, or else I'd be shaking when I'm soldering, and that wouldn't be good. Okay, let's raise the bottom a little. I think it's gonna be okay, but just to make sure. Yeah, it's fine. Okay. Okay, this screws in the back. See a wire here that appears to be loose. That was probably an external speaker wire. I don't know. We'll figure that one out. Maybe somebody has been in here. Okay. And that's the back cover. Now we slide the chassis out. Nice tight fit, I like that. Okay, case has got some dust. We'll clean that up and see about turning that dial so that it's facing the right way. And there you have the unit. We have a cardboard case on the capacitor. Got a little bit of corrosion there. The metal case is underneath, but we'll get to that. You can see it definitely needs some cleaning. Speaker is in really good shape. I don't see any issues there. And there's the dial. And look at that, they sealed the case all the way around to keep out as much interference as possible on this radio. It's a very nice radio. Yes, and this is for the external antenna, should you wanted to add one. It has a built-in broadband broadcast antenna, AM antenna there. And it's a All-American 5, has 5 tubes, 4 glass tubes and 1 metal tube. And let's see, schematic calls for, as a 12B-E6 or a 12SA7, 12BA6 or a 12SK7, depends on which model it is. This covers 5 different models. 12AT6 or a 12SQ7, 50B5 or a 50L6. It's a GE tube. That might have been exchanged at some point from these glass tubes. Let me see. No, maybe not. It's a GE. That's a National Union Electrics. And it might have been just using up some of the tubes they had in stock. It seems like these two are National Union. This one's a National Union. This is a GE, and this is a GE. So they might have changed the couple tubes. This is the 50L6, so that would be the audio output tube. And here we have a 35Z5, which would be the rectifier tubes, but not always. And then the other tubes are in the oscillator and the detector and preamp. Okay. So the first thing we're going to do is check the capacitor, filter capacitor. I'm pretty sure that's a Ghana. Let's take the bottom off. I guess it looks cute. Yeah, that'll work. And these are, look at that. That's a really neat job. These are brass threaded cylinders that are attached, riveted to the bottom of the case for the screws in the bottom of the radio. Quite nice. Very good design. Solid, and I'm sure that interference is really low on this radio because it's got a sealed bottom on the chassis. It's always the last screw that gives you the trouble. So you really I should really figure out which ones I want to take out first and then remove the last one. Oh, looky there. Isn't that cool? They actually give you the original schematic diagram in the bottom of the chassis along with the tube layout. Man, let's compare these. This is interesting. So we will set that up for a second. Actually, just going to set it just like that. Make sure that tube's in there. Set that just aside for a second, and let's look at this. Here's the schematic from Riders, which covers multiple models. And here's the schematic that's actually in the radio. Wow, what similarity. On here, can you see all this? Yes. On this, you have multiple tube assignment numbers based on which tubes are used. You notice that? That makes it it's also test points. Makes it a little complicated to read because you got all this overkill here with these triangle dot numbers. On the plate, we have just a normal tube with the numbers on there, easy to read, and arranged. The tube numbers are arranged in the order that they need to be in. Okay, so here we have a 12SA7, a 12SK7, a 12SQ7, a 50L6 GT, so that was replaced, and a that's what's in there, I'm sorry, 35Z5 rectifier tube. So what we have is the bottom numbers on here: 12SQ7, 50L6, 12SK7, 12SA7, and the 50Z5 instead of the 35W4. The schematic looks identical. I don't see any, oh, I do see some issues. See here, this one has a 100 ohm resistor. It's only used on the 12BA6 tube. Well, of course, we got the 12SK7 tube, so it doesn't have that resistor. This is the advantage of getting accurate schematic. You don't have all this double talk for these multiple schematics, but so far that's the only difference I see. Very good, very good. Pilot light. They're all exactly the same. We get the filament string. So the only variation is the one that they mentioned here as being only on the 12BA6. They use this current limiting resistor. The tuning capacitor is the same, and the alignment procedure, I would imagine, is the same. They even give you the alignment procedure on here. A little bit of dust, but it looks identical. So I'm assuming it says the same thing without actually reading through it all. They do have a note on here that I'm not seeing on that schematic. But this schematic has a note here. Probably the same. All DC voltages measurements are made with 20,000 ohms per voltmeter from circuit common bus line. And that's right here. And then these two are the same. It's hard to read this one. It's a bad printout. On some productions, talks about a 220 ohm. I can probably see that a little better with my magnifying glass. Let's see what that says. On some productions, R6 and R11 is 220k ohm resistor. R2 is a 10 ohm. R8 is a 220 ohm. So if these resistor values are different on the chassis than they are on here, that just tells you the difference. And then condensers are listed here, which are listed right there on the board. I don't know if that helps you see anything in there, but it helps me. All the resistors are plus or minus 20%, as I'm sure are the capacitors. And we will check through it. But there you go. We have the actual schematic that was assigned by Gilfillan Radio Corp in, I believe it was Los Angeles, California, was their headquarters. I don't see it on here, but I believe that's where they were located. Anyway, okay, so back to the radio. And we might refer back and forth between the schematic and the radio. So one of the first things I like to do when I'm working on a radio is, because we're looking at everything from upside down from the schematic, is to mark the tube on a piece of paper, the tube layout. And I do this for the bottom view. And it just makes it easier. I have seen a video where a radio was shot on one of online YouTube video, and what had happened was they actually switched the output tube with the rectifier tube. They had them in reverse. Somebody had worked on the radio, and of course that blew out the output tube and did a job on both tubes. So we don't want to do that. So what I'm going to do is transpose these from the way they are on here, which is the tube layout. So it shows you, and this is what I do. I draw it out, but I draw it out upside down. So basically, from the bottom, when we flip it over this way, the speaker is over here. we have a tube here and a tube here, and we're going to have a tube here, and next to that tube we have a IF can, and behind that tube, IF can, we have another tube sort of skewed, and then we have another IF can. And you notice I'm drawing it just the opposite of where they're located. And then we have another tube here. And here we have a filter, our gang condenser. And we have our two controls for that. The volume control and the tuning string. Okay, so what are these tubes? Well, if we turn it back the way the radio would be, it would be like that, because we're flipping it this way. This tube is closest to the speaker, which is the 50L6. So that's the 50L6. And the one furthest from the speaker is the 35Z5. And then back here next to the speaker, this one here, we have a, let's see if I can see it better on this one. It's going to be the 12SQ7. So that's a 12SQ7. And here, which would be this one here, is a 12SK7. So that's a 12SK7. And over here we have our 12SA7. So that's a 12SA7. And by doing that, when I flip it over, I don't have to guess. I know this is the 50L6, this is the 35Z5, 12SQ7, 12SK7, 12SA7. So you see how that really helps, so you don't get confused when you're flipping it back and forth. Anyway, word to the wise. So we'll put that there where we can see it, and turn this around this way so the speaker's in the front. We'll do the same thing here. Though the numbers are upside down, it don't matter, I can read them. I don't know, that might be original. This capacitor, you see that, it got pretty hard. It's kind of baked there. Don't even know if we can read the numbers on it. Oh, it's a Sprague 0.05 400 ohms. Looks like these solar capacitors were the original, and perhaps somebody replaced a couple of them. That looks like it might be a solar. Yeah. Somebody replaced a couple of them. This is a giant 500 ohm resistor, power resistor right across the capacitor. And we got another capacitor down there that is not a solar. So these two look like they might have been added. I don't know, that could be factory again, using parts they had in stock to try to use them up. And since the owner said there's a hum, I'm going to assume that the output stage works. And we'll verify that too. Okay, we got an issue, and I found common. Common is here. That's this line here. It comes off the switch. So it comes off the switch by this red wire here. If you trace the wire, it comes to this grouping of capacitors and everything, and I kind of figured that was common, and sure enough it is. When the switch is on, that's common. This is not a hot chassis from the line cord. It has a 0.25 capacitor that goes to the chassis ground and a 270K resistor that goes to a chassis ground. Now, normally this would be considered a floating chassis. It's not a hot chassis. However, if this capacitor shorts or this resistor shorts, then common is brought down to chassis and the chassis becomes hot. But as long as those values are not shorted, those components are not shorted, this stays at a voltage above. In fact, we got 270K ohms from the common, from the line cord to ground. Now the other side of the line cord is to the plate of the 35Z5 or 35W4, depending on what unit, in this case 35Z5, and the cathode, well, this is a diode, so the cathode becomes rectified at 110 volts, and that's your B+. So this is common, this is B+ here, which supplies the coil, the output transformer for the output tube. Now here's the problem, and I don't know why, because I have to check out the issue. I noticed on my tube layout, when I made this tube layout, I made it from this drawing here. So we have a 50L6, a 35Z5, and a 12SQ7. Oh, but that's not the case. Okay. On this one, if we look at it, we got a 50L6, a 35Z5. That's not the case. This is I made from the actual tubes. So we got a serious issue, because here's what we got. We got one diagram telling us that near the speaker is the 35W4, and away from the speaker is the 50L6. The diagram that came with the radio, which I would put more emphasis on, has the 50L6 output transformer right near the speaker and the 35Z5 out at the outside corner. So you see why I like to draw diagrams. Out the outside corner of the chassis. These are saying exact opposites. Okay? Now here's where the problem gets even more interesting. Both of these have all of the other tubes in the same place. Okay? The only thing that's different on this entire tube placement chart is the placement of those two tubes. Right? Now, we're not going to use that, we're going to redo it again. On this unit, which I have not plugged in, notice the 50L6 is on the outside and the 35Z5 is near the speaker. We've already noticed that some of these tubes have been replaced, so someone has come in and changed these National Union tubes and replaced two General Electric tubes. Okay, but they have the 50L6, the outside corner, 35Z5 near the speaker. 35Z5 near the speaker, right? On this, they're saying the 35Z5 is in that outside corner, and the output tube is at the speaker. And this is what I talked about before, how some things can be reversed. These tubes are set up the way it shows on Ryder's schematic. which is the opposite of what this unit says. It is very possible that when somebody serviced this and replaced those tubes, that they didn't open this case, in which case they would not have seen this schematic, and they would have went by riders and put the tubes in the wrong place. And that is, I don't know if you can see that, but that is a big problem. They say exact opposites on the rectifier and the power tube. Now, is that a problem for us? No, not really, because we know that regardless of where the rectifier tube is, it has to connect to the filter capacitors, because this is your power supply, and it has to be filtered to produce a smooth, unrippled 100 volts DC. So the capacitors connect to the pins on the 35Z5, which is the same thing both diagrams show, because that's part of the power supply. It has to be there. So we know that the capacitors connect through a 500 ohm resistor here to pin 8 of the 35Z5. So if we follow the output of this two capacitors, there's actually 3 capacitors in this can. There's also a 10 microfarad. So we have a 40, a 60, and a 10 coming out of the bottom of this can. This is called a floating capacitor, or an isolated capacitor, because it is not, the metal case of the capacitor is not connected to the chassis. It's isolated from the chassis. So if I pull my ground lead here off, if you look here, you can see well, first off, you see this insulator at the bottom of the capacitor, which insulates the capacitor from the chassis. Then we see that the twist tags, there's 3 twist tags. You probably can only see, maybe you can see that one there, this one here, and there's one back here, and they all twist to this plastic insulator, which holds the capacitor to this insulator. This one is the ground of all of the 3 capacitors in the can, and it comes up here and ties to this bundle. So we know this is common. This is the common connection, and all the measurements are from there. So if we follow this, it has 2 wires coming out. It has a green wire here coming out, which comes over to this bundle, and from there it goes to this same green wire coming back over here, and it connects to here, pin 1, 2, 3, 4 of this tube, whatever this tube is supposed to be. According to our chart, it's supposed to be, to the schematic that came with the radio, that tube is supposed to be the 35Z5 rectifier. So if we follow it, it's pin 4. If we look at this, we see that from these capacitors, there's nothing going to pin 4. We have 5, 8, and then the filaments are 2 and 7 with a center tap on 3. So why are they going to pin 4? 1, 2, 3, 4. It's going to pin 4. Might be just a junction point not being used, connects to this red wire here, which comes around here, and sure enough goes to the filter capacitor, which is, to the output transformer. So it goes to here, which does tie to pin 4 of the 50L6. So you see they go through that 500, they come up 100 volts, goes to there, and it also goes to pin 4 of the 50L6. So where this connects to pin 4, this should be the 50L6, and it is. So it is correct. But the tube layout on here is wrong. The tube layout on this one is showing, it's a misprint, it's showing the 50L6 near the speaker, which would be here. So I'll flip it over. It's showing the 50L6 as being near the speaker. That is not correct. The 50L6 is here. We just traced it and we know that that's the case. So in this particular case, Riders is correct, and the schematic that came on the bottom of the unit is misprinted. And to verify that further, we can follow the other side of this 500 ohm resistor. So this 500 ohm resistor on the one side goes to the output transformer and pin 4 of the 50L6. On the other side, it goes to the 35W4, or the 35Z5 in this case, and it connects to pin 8 of the 35Z5, as well as a 40 mega the filter capacitor. So if we come back to the other side of this, we see a red wire coming out. And that red wire comes around, comes over to here, and connects to pin, it looks like it's going to pin 7 anyway. Here, pin 8, there it is. It's going to pin 8, and so this would be, pin 8 would be the 35Z5, and when we look at it, 35Z5. So the tubes are not in the wrong place, but the diagram is misprinted, and the Riders diagram is correct. Amazing. I would have thought this one would have been correct. But now, had I not printed out Riders, and I was working on this radio by this and this tube layout, of course, I would trace this anyway, because I'm checking components. But had I just gone by this and looked at the chassis, I'd have said, oh, those tubes are in the wrong socket, switched them around, and blew them both up. The things we have to go through. Anyhow, what we're looking at is these two filter capacitors here. Does this thing even work for you guys? I don't know. This capacitor needs to be cleaned up. And to do that, I'm going to have to do it off camera. I'm going to have to replace those 3 capacitors. I'll leave the can in. Unfortunately, I couldn't get this cardboard sleeve off. It's like really stuck on there. So I'm just going to leave that intact because I don't want to ruin the cardboard sleeve. Underneath the actual metal can would tell me what the resistors, the capacitors are, and which one is which, but I can just trace the wire and figure that out. So I'm going to go ahead and start by changing those 3 capacitors, and then we'll go from there. This capacitor I know is short. In fact, we could go ahead and check some capacitors while they're in circuit. Let's do that. So I'm going to use these alligator clips because they do a much better job of making a good contact. So what I do is I put those alligator clips on the test leads here, and I can just clip them across. So this guy here is supposed to be a 0.05. So if we clip that on there, put this on, and I'll put that down where you can probably see it. It's on capacitance. And we got roughly 28 microfarads, where we're supposed to have 0.05, 5/100ths of a microfarad. So that guy's shot. He's toast. This one here is 0.25 microfarad. So we clip it on there, clip it back on this side. And that one's open. It's nothing. It's nothing. It's dead. Oh, there we go. I got something. It went away. It's open. It had a nanofarad. Yeah, that one's open. This one's shorted. This one's open. Let's see what else we can find. And this one's high, and that one's open. Those are the only two wax capacitors that look different than the others. There is one other one, and that's that one down there, which is another 0.05. Let's see if we can get on that. They have the shield band on this side. That don't always mean anything, but let's go ahead and put the negative on that side, and the positive goes right to the line cord. And that one is, if it stabilizes here, it's around 30 microfarad. Okay, it's charging up the capacitor, but it's around 30 microfarad. It's supposed to be 0.05. Now let's try some of these solar ones. This one is a 0.01. And you know, some of these, the values would change if I desoldered them, but just check them in circuit. This one's good. It's 12 nanofarad, so yes, 0.01, and it actually tests good. Amazing. This one is, oh, it's got some goo on it there. 0.01, another 0.01. Look at that. Nope, there we go, 0.01. If we go to that microfarad range, there we go, 0.01. So these solar capacitors are quite amazing. So far we found two that are bad for sure, but they're not solar. Alright, let's try this one here. It goes to chassis ground. It's measuring 0.1 microfarad, which is well, yeah, it's not intolerance. It's a 0.25, and we got 0.9, so it's shot. That one's shot. It's too high. Let's try this one down here. I think it connects to the same place, and it goes to there. 0.05, and that looks like about a 0.05. It might be a 0.01. Let's see. See if we can turn it enough to read it. Can't read that one. Almost, but it's probably okay, because that's a common size 0.05, and I'll know when I get some of the other things out of the way. Let's see what this one is. This one is a 0.05, so that's probably a 0.05 as well. And let's check it. So basically, if that's correct, we have 3 capacitors that are connected together on one side. that one's open. That one's open. Might just flip them off. No, it is loose. Let's tighten that up. No, it's open. Check these again. 0.05. This one's supposed to be a 0.25. And it's 0.9. It's almost 1 microfarad. That really is pretty big for a 0.25, but that's what it says on it. 0.25 at 200 working volts. So this is another 0.25, and it's the one that we said was short. Let's check it one more time. See if everything's still reading the same. Yeah, it's open. It's probably shorted. Let's see if we can get some resistance on that one. It's all over the place. Yeah, it's shorted. But it's actually charging up. So it's around 300 ohms. It's leaky as can be. And I would imagine that those were replaced the same time those two tubes were replaced. Same thing with this 0.05. I'm sure the resistance on it is going to be leaky, leaky, leaky. Yeah, 200 ohms and dropping as it charges up. Let's see if this one will hold the charge. I doubt it. Well, it's charging up. It's up to 1 meg ohm. That's pretty nice. Still dropping though. It's actually, they charge up and they from the battery in the meter, and it's actually trying like to reform itself. Of course, with no power, you can't reform. It has to be high voltage. And these things are short. They're not going to reform. Okay, so we got a couple good ones, and we got some not so good ones. Now, like I said, sometimes when you take them out of circuit, because they're no longer in parallel with other strings of the circuit, they may read a little better, and I'll check them that way. This one reads fine. I think it had some glue on it. I think that's just, that don't look like wax. It's hard. It looks more like glue. So they probably had this glued or drip some glue in their resin when they were soldering the connector. Yeah, that's what it is, this dried resin from the solder itself. But this is short, this is short. Filter capacitors are short. I'm sure that one down, that 0.05 down there is toast. And the rest of it don't look bad. I think the biggest thing is changing out some capacitors. So there we have it. I'm going to go ahead and switch out those caps, and then we will power it up and see what it does. Filter capacitors in. I put in a tie strip here and was able to tie the resistor that goes across the capacitors to it, and the 60 microfarad, which is, by the way, 68 microfarad, that goes to common. And I got the other one in over here, the 40 microfarad. It's in, and this was a capacitor that was short. I had to reroute one of the wires for the strip. So I cut this capacitor, because I know it's short, out of my way to deal with that. Now the filter capacitor is totally disconnected, the original filter capacitor. I'm jumping from here back to where it solders. I didn't want to solder it back because it's big and bulky and it's coming out anyway. but we can go ahead and see what happens. I got my meter here. I'll put that down so you can see it. Well, we can measure the B plus. That probably helps better there, I don't know. But you can see the B plus as we bring it up. We'll see what it comes up to. I'm on a current limiting bulb and my variac. So let's see what we get. Bringing up the voltage. And the switch, I believe, is on. Yes, the switch is on. Still difficult to turn. We're at about 55 volts. And we've got no B plus yet. That's okay. That just means the tubes haven't lit up yet. Let me take a look. Oh, forgot. A little bit of voltage there. I took out the rectifier tube while I was soldering on that socket. Okay, let's try that again. So we're back up to 55 volts. We still don't have any power yet. Okay, I'm still seeing a problem with the B plus. So we'll have to figure that one out before I can shut my current limiting bulb off. Okay, we have voltage coming up. I think I just had the plug loose. I'm currently at 75 volts, and we got 56 volts of DC, and still climbing. The dial light is lit. You can probably see it there. Still climbing. I'm going to bring the voltage up a little more. Tubes are conducting. The voltage should start dropping. Okay, we got 74 volts of B plus. We got rid of the hum. And then the voltage check drawing 180 milliamps and 16 watts. Not bad. So I'm going to bring the voltage up the rest of the way. We're up to 110 volts. It's giving us 90 volts of V plus. Okay. Now, of course, I'm in my basement, so I don't get a lot of signals. Something there far away. Probably WNEG in Toccoa, maybe.
Elected leaders in Houston are scrambling after yet another resignation of a city official. Remaining city councilman.
Accurate is just a click away. Simply go to the Access WDUN weather page and enter your zip code. It's weather wherever you are at accesswdun.com. Presented by Hardy Chevrolet and powered by WDUN.
They brought the voltage up to 115, which is giving us 91. We still got some voltage loss through these old capacitors. They're going to have to be replaced, the ones that are bad. Sensitivity is pretty good. It's trying to grab some stations that are way out there. And those are pretty far away stations. This is Cornelia. Okay, so we got some power going now. Let's shut it down. And I'm going to go ahead and change these capacitors that are bad. Okay, it's time to start changing some capacitors in here. This is the first one that we had already clipped out to make room to get to solder those guys in. And you see it's supposed to be a 0.25 microfarad. It's registering 3 times that, 0.764. Here's a 0.22. You know, the standard microfarad values of capacitors have changed, but it's not a big deal as long as they're within tolerance. You see it plays even with that outrageous tolerance, way out of tolerance. Here's a 0.22 that we will use to replace it. And you see it registers 0.223. So let's grab my calculator here and we'll find out. Okay, so a 0.25 plus or minus 20% would go all the way up to a 0.3 and down to a 0.2. So these are in tolerance of the 0.25 that was in there. So that's what we will use to replace that guy. And this is a very tight box because of the way it's made and with the seal. So I wasn't able to do what I normally do, which is strap these and make them look better. I'm more concerned with their ability to stay cool, not short out. I put some shrink wrap on them, and I moved this one from the can over to, it goes across this resistor and across 2 pins of the audio output tube. So I'll clean that up a little bit once I got to dig in there and get that wax capacitor out of there, and this one, I'm sure they're bad, but we'll check them as we go. So this one goes from common to the center of this, And I'm going to go ahead and do these off camera, but I'll show you the values of them as I go. So like this one here, it's baked. We know it's bad. It's a 0.05, and it goes to common. Let's clip that one. We'll clip it from the common side, and I'm just going to leave that right there so we can see where it goes and connect it up. It should be a 0.05 microfarad. And what we got on it is 0.15. So again, 3 times what it should be. That's quite a bit out of tolerance, and yet this radio has been playing good. That's why we have so much voltage drop on the B plus line. Not only do we have voltage drop, we have resistance on these. They're bleeding like crazy, so the they're acting more like a resistor than a capacitor. A capacitor is 2 plates, an anode and a cathode on electrolytics, and just 2 plates on a regular capacitor. And nothing is supposed to jump that gap but AC. No DC is to go through there. That's what it's for. It's called a filter capacitor, or filtering. And they filter the DC out and allow the AC to go through. And from stage to stage in the amplifier, both the IF, the RF, the mixer, as it goes through each, the detector, and then the preamp and the output amp, as it goes through those, each stage is an individual circuit. And you can see that on the schematic. You can see how, excuse me, how you have your antenna where the signal comes in. Then you have your detector stage and oscillator stage, and then you have an IF can, and it's inductively distanced from each other, just like capacitors distance from each other. And so AC can go across, but DC can't. And that's junction to the next stage, which is separated by another IF can. And then over here you have your preamp stage. And then now that one is separated by a capacitor only, going into the control grid of the output transformer. And then that's separated from the rest of the circuit, and it goes through the output transformer coil and goes to the speaker. So you see how each group is separate. The power supply is also is separated. You can see that easily because they draw it separate to make sure that you understand that the only thing that goes through is your common line, which is your reference point, and B+, which supplies the plate voltage to each of the tubes. It comes up from B+ here. It goes up to the through this IF can, goes to the plate. 100 volts goes to the plate of the first tube, and then the second one, same thing, comes up from the 100-volt line, goes through the IF coil, and goes to the plate of the 12SK7. And then here, same thing. So, and this one actually goes through 2 voltage divider, a couple resistors in series, which drops the voltage down to 60 volts, and that goes to the plate of the first preamp. And then the full voltage goes through the output transformer and supplies, there is a resistance there, so it drops it down and supplies 85 volts to the plate of the output tube. And so, from the grid to the screen grid to the plate, we have a drop of 15 volts. But each section is independent. But when you have bad capacitors, it's like shorting across the capacitor with a resistor. It's like taking them out and putting a resistor there. So these, they're just bad. They're just leaking and they're acting like resistors. So they need to be changed. Even the ones that are intolerants, like these are intolerants, are probably leaking DC. And we can check that with an ohm meter across them as we go. Actually, let's see what we got here. If we come across this 0.05 and put this on ohms, it should be way up there, like 50 megohms. And you see it's jumping all over the place. It's actually leaking electricity through DC through the capacitor, and it's just fluctuating as it's going. It's just jumping all over. That capacitor is toast. Let's try this one. Actually, that one measured open. This one is measuring roughly 500K, and it's picking up a charge, so it's jumping around too, but you see the same thing. That should be a dead, unopen connection. If we take a good capacitor, and we put this across a good capacitor, measuring resistance now, not voltage. Look at how it's climbed. It climbed all the way up. I'll do that again so you can see it. I'll just reverse it. It's going to start out real low because now it has a charge on it. Actually, I could take the charge off the screwdriver here. Okay, charge is gone. So and I'll connect it the other way to make sure the charge is gone. And you watch the resistance. We're in the megohms right now. Look at that, 5, 10, 14, 29, 30, 40 meg, 50 meg, and then off the chart. My meter won't even measure above 50 megs. So it'll measure up to 50, actually it'll measure up to 60 megs. And it's past that. That's a good capacitor. So you see how this will not leak DC. DC cannot get through 60 megs. Ohm's law is voltage, current equals voltage divided by resistance. So we got 100 volts. So if I look at my calculator here and I type in 100 volts and I divide that by 60 meg, 60 with 6 zeros, I got 1.6 times 10 to the minus 6, or 1.6 microamps. We're talking no current flow at all. As far as this radio is concerned, there's no current flow at all. 1.6 microamps of current times 60 megs is no voltage. I mean, there's no current going through there. So, I mean, it's what it's supposed to be. So those capacitors are leaky. Even the ones that test good are going to be leaky. They may not be as leaky as these, but they're going to be leaky. So some of them, actually, if it was up to me, I would change them all, but that's up to the customer. He wants the radio working and keep it as original as we can. And I understand the logic in that, but these capacitors that are that bad, they got to be changed. So I'm going to go ahead and start changing capacitors and continue the video when I get to the one that actually checks good. And I'll show the capacitors, what they do once I cut them out and replace them. But anyway, I will continue soon. Okay, I've been going through these capacitors and I've replaced the ones that are way out. There's some others that are out. Some of them test pretty close. But I wanted to show you something. I disconnected this one because it read really high. It's a 0.25 at 200 volts. So if I put the meter on there, and it went to chassis ground. It's supposed to be a 0.25. It's a 0.82. So here, if I connect it back where it goes to 0.89. So it's out of tolerance. It needs to be replaced. Okay, so whether it's connected or disconnected is irrelevant. But this one here is a strange one. It shows you what I was saying before about testing them in circuit. Right now it's saying overload. It's a 0.05. So if I go to range and go to full microfarad, it's saying it's 115 microfarads. Well, obviously it's not 115 microfarad, but that's what it's saying. So if we take it out of circuit, and I just tacked it back in, let's take it out of there. Okay, now if we look at it again with it out of circuit, it's 0.1. So if we go to range, we get a more accurate reading. So it's a 0.08, 0.86. It's bad. It's supposed to be a 0.05, but you see the difference. And this tube is out, yet there's still other parts of the circuit. So if I connect it back into the circuit here, it goes to overload. And of course, if I go to the range, it shows it as 115 microfarad. So that shows you can't always test a component in circuit. If one, you can, but if a component, a capacitor tests bad or a resistor tests bad in circuit, you have to unsolder one of the sides to do an accurate test. So before I cut them out, this is what I do. I went to cut that one out because I knew it was bad. And when I checked it, it was still way bad, but it was no 100 and something microfarads. This one I knew was bad because it was saying 800 and it's a 0.25, and I cut it out and it's a 0.8, I mean, and when I cut it out it's still around 0.8. So those two got to be changed. This one here is a 0.05. And it's good. It tests 0.056. So 0.056, it's good up to 0.6. Now that doesn't mean it's not leaky. That just means that the capacitance value is accurate. These two are way out of tolerance, way out. So I'm going to go ahead and replace these, and I need to get with the customer and tell them it'd be better just to do a cap job and replace all of these, because they are so far out of tolerance. And we're talking 1, 2, 3, 4 more than the 5 I'm doing. So, you know, I'm doing half of them. I might as well do them all and protect this radio, but again, that's up to the customer. So we'll go from there. But I wanted you to see how in circuit, out of circuit makes a difference. I'll continue the video once I know what I'm doing with this unit.